Hello and good evening, everyone. My name is Shiva Ramrit, and I'll be your host for today. So welcome to PyData Trinidad and Tobago's 17th session. And before we begin, we're just going to go over quickly the PyData Code of Conduct. So be kind to others, don't insult or put down others, behave professionally, and remember that harassment, sexist, racist, or exclusionary jokes and language are not appropriate for PyData. All communication should be appropriate for a professional audience, including people of many different backgrounds. Sexual language and imagery is not appropriate. PyData is dedicated to providing a harassment-free and event experience for everyone, regardless of gender, sexual orientation, gender identity and expression, disability, physical appearance, body size, race, or religion. We do not tolerate harassment of participants in any form. Thank you for helping make this a welcoming, friendly community for all. So let's begin by introducing today's speaker, Mr. Kyle Freitas. So Kyle is currently a machine learning engineering lead at Block, working on AI solutions for identity verification in Cash App. He held senior and lead software engineering positions at DESA, and he also lectured a multitude of courses at the UW St. Augustine, where I was thankfully able to meet him and learn a lot from him. While also at the UW, he was the lead software developer for a multitude of initiatives across the Caribbean in areas of agriculture, fisheries, and education. And his experience in mentoring and teaching young software developers spans almost 10 years. So without ado, I'll open up the floor to Kyle.
Hi, Shiva. Thanks a lot for that introduction. I do think that is really something coming from you, and I'm really happy that you were the one who did the introduction today. I guess good afternoon, everybody. So this is going to be I hope, short talk. I lost track of how much slides I had from the time that it went to review and it got cut down to the point of where we are. But hopefully this is going to be a short presentation. I just kind of like walk you through a little bit about how we do development specifically within the domain of machine learning using the Apache Beam Python SDK. So again, just quick context, as Shiva mentioned, I'm an engineering manager. Some people call senior or lead, whichever word is suitable for you. And I work specifically in the area of applied machine learning in the domain or the stream of identity. Cool. So Cash App. So maybe I should have had a slide before this, but just generally speaking, the company that I work for is Block. Block has several small business units. One we typically know as Square. That's the one that most people sort of recognize because it's been around the longest. And then there's Cash App. So Square sort of deals with like the merchant or the businesses that are interacting with people, and Cash App deals with the individual user and providing services for that user or for that individual. And Cash App has a vision, and everything that we do, we often emphasize the relationship to that vision, and has set out sort of as Google has become like a verb for people who wants to find information. Cash App aims to redefine the world's relationship with money. Again, that motivates why it's investing in crypto, it's investing in P2P and all these other areas that it operates within. Generally speaking, most of the times when people hear of Cash App, they think of peer-to-peer, or even most recently, they think of crypto. But really and truly, Cash App is more or less like an ecosystem of tools. So there's a lot of capabilities within this single application, and all of it is focused towards economic empowerment and growth. Some of the capabilities that it provides are things like peer-to-peer, fractional shares. As a matter of fact, it probably was one of the first companies to introduce fractional shares, and has the ability to buy crypto. In this case, they made a strategic decision to only support Bitcoin. And again, you can do things like microloans, so you could get small loans at a reasonable rate, again, as an attempt to sort of disrupt the industry that surrounds payday loans and that sort of like predatory system that keeps people in a cycle of poverty. Cash App at this moment in time is primarily focused in the US, but again, it has other offerings in other countries. For example, in the UK, there is peer-to-peer transfers. So you could transfer money cross-boundary between the US and the UK without having to pay the exorbitant fees that you typically have to do for wire transfers. Within that org, I forgot to ask, do we take questions in between or at the end?
Presenter's choice.
Okay, I'm good with questions at any point. So again, if there's anything, let me know. I'm not sure if I'll necessarily see the chat, but I'll try to keep an eye on that in case anybody asks a question. But again, anyone feel free to let me know if there's a question that I need to address. Within that cache group in Cash App is a relatively large organization, depends on the frame of reference. It's small compared to like Facebook and Google, but it's large compared to many other companies within the space. There's an entire organization dedicated to machine learning. Technically, it's machine learning and data science. There's a sort of like distinction between those two. Data science sort of like focuses on the capabilities, the analytical processes and stuff that drives a lot of what Cash App does, from its mobile feature offering, even right down to the actual server engineering capabilities that we develop. All of that is driven from data, and the data science org handles that specifically. The AI and ML teams primarily focus on what we would traditionally think of AI, and they're using all of the techniques that you could think of, from the all-powerful decision trees to deep neural networks to graph convoluted networks. We're using the whole range of ML suite to be able to protect cache customers, to protect cache itself from harm, and of course to add value to the customer's experience. One of the important things, and again, just context to appreciate just a little bit about what we do, is that it's a matrix organization. So like my team, for example, we would interact with several teams across mobile, platform, product is the ones who sit down and say, hey, this feature is the feature we're going to build. And so we work across all of those domains. The domain I work with is specifically the domain of identity. We have two groups. So I'm applied and there's modeling. What's the difference between those two? So applied focuses on the ML lifecycle, so the entire process of machine learning, while the modeling are sort of like the core practitioners who sit down, create, the experimentation, try out the different algorithms and stuff. And it's sort of like a collaboration between those two teams to come up with a final solution that we push into production. In our team, identity, it's the main focus of our team is to build confidence in a person's identity. That's sort of self-explanatory, but we have two broad areas of focus. One is to keep the bad actors out. So as you could imagine, Cash App is a financial institution. There are a lot of people who are trying to get in under either false identity, trying to Photoshop somebody else's identity. We've seen a lot of deep fakes. For example, recently, we've also seen very strange things like people using doll heads. So they literally like take a picture of the doll, put it on top of somebody's ID, and then hold the doll by its head up in front of the camera to attempt to pass identity verification. So again, we see all kind of strange things, and part of our job is to keep those bad actors out. And also the other part of it is to allow what we refer to as the underserved or the underbanked group of people into Cash App. And just to explain underbanked just a bit for Caribbean context, is that there's a lot of people who, for one reason or the other, are not able to access traditional financial services because they have no credit history, they don't have a proper form of ID. The question is how we could actually use machine learning to bring them into the ecosystem so that they can have access to financial tools to improve their economic position, the social status. So that's the background. So let's jump into the problem space. So again, for obvious reasons, I'm not able to go deep into the specific nature and types of data that we use, at least not for this presentation. Maybe in the future, that's something that we could do. And part of the reason is that this is like work that is currently in flight. So there's some protection around it at the moment. And to give you a sense of what we deal with, we typically look at, we have three big Vs, right? These are the typical big Vs of big data. So in terms of a volume, right, we are processing around 150 to 200 gigabytes per day. That's the P50, that's the 50th percentile. Gets larger than that as we go like to P95. I think P95 is something like almost like 1,000 gigabytes, 1 terabyte, right? Which is kind of crazy when you think about it, but that's how much we process in a day. We have a velocity, or how many new records we're getting on a regular basis, or around 200 million new records daily. So that translates to around 3,000 queries per second. So in other words, any system that we build in the 50th percentile, again, the P95 and the P99 are much higher, but again, I'm just giving you a sense of what we have to consider. We're dealing with about 3,000 queries per second. In terms of the variety of the data, the actual structure is consistent because it's coming from the mobile device, and the mobile device basically says, hey, here's the data, here's the format that the data must be provided in. However, that data is very messy, right? It has a lot of null values, it has strange values because of the nature of the data, things that you don't expect, and that just is a pain to deal with. And one of the challenges that we have is that we actually have a lot of duplicates, some of which are duplicates that are representative of bad activity, but some of it's duplicates because of the nature of, a device over an unstable internet connection, among other things. In total, so again, the 3 V's we talked about before, in terms of like the considerations that we need, especially when we're thinking about streaming. So our solutions are typically streaming, but the need for us to do sort of like batch operations, and that batch operations typically has to be done over the entire data set from the beginning of time to the current snapshot. And as of June, when I checked the data yesterday, we have about 50 terabytes of data and about 80 billion rows as of June 2020. So again, that's not the biggest in the world compared to like YouTube, but it's fairly substantial. And it's an interesting challenge for us to solve. Within that space, as I mentioned, we think about 2 problems. We think about the actual problem of feature generation. And as I mentioned before, our pipelines are typically streaming. So as data comes in, we have to process that data and make that data available for training, for evaluation as quickly as possible. So we generate a set of features and put those features in a form that they can be easily accessed. And as I mentioned before, we have cases where we might add a new feature, we might add a new transformation, and then we have to run a batch to be able to recompute the features at that particular point in time. So again, we have to think about those 2 considerations. We also have to think about the actual evaluation. So again, we have the model in production, and that model can either be on demand or real time. Again, you can also have things like batch models. So you could have like a model that runs at a regular cadence and produces a set of inferences that are then consumed by service in production. However, in our case, because we fall under the category of risk, and from an identity standpoint, most of our use cases require us to have, the inference be on demand, meaning that as a request is made, we could actually just simply compute the evaluation. It's sent to a model lives somewhere in memory or in a service in the cloud, and it gets back a response. And real time sort of like deals with, okay, if an operation was done a couple minutes or seconds, in some cases seconds, but in my use cases, it's minutes. That action produces a set of signals that are features that are available for the model at evaluation, and that's what we refer to as a real-time evaluation. So that's sort of the problem space that we have to deal with. And again, we're faced with this. This is a novel data type. There was no precedence, no prior art. We were like, all of these things we have to think about, and what are we going to do? For this presentation, partially because of time, I'm only going to focus on the feature generation and how we use Apache Beam and the Python SDK of Apache Beam to be able to deal with the stream and batch operations. So many of you, I'm not sure, I wasn't entirely sure of the audience, so I kept this as high level as reasonable, but at the same time, providing some nuggets that I think would be valuable even to practitioners, is that many of you are familiar that there are many tools available for dealing with big data or large data, and to do that both for batch and for stream, right? Again, I don't know if I define batch and stream. So batch is sort of like you have data and you could say, okay, I could take this group of data and I could process this group of data at a particular time. So you could think of like, if we're getting all of that volume of data, then we could say at the end of every day, we're going to process all of the new records that we got for that day. That's what we would refer to as a batch. So we process incoming records on a day-by-day basis. That's a batch model. A stream model says that as we're getting the data, as it's coming in from whatever systems are providing it, we're processing that data as soon as we get it. So there's almost as you could think of like a continuous pipe, hence the word pipeline. There's a continuous pipe that is just taking data from one source and writing it to another that is then used for other ML use cases within the organization. So that's the difference between batch and streaming. Beam, according to its own website, provides us with what is called a unified programming model for batch and stream data processing pipelines that simplifies large-scale data processing dynamics. What that basically means is that, which is the first point, is that it provides an abstraction to all of the underlying challenges associated with distributed processing. So before Beam, I shouldn't say before Beam because we still do this, right? You have to think about like distributed file systems. You think about like your Hive and your Apache Hadoop based operations to be able to figure out how to transform data across these different machines within a particular cluster. However, Beam just basically takes all of that and abstracts all of that away from you so that all you need to think about are the specific operations that you want to perform on that data set, and it just hides away the complexity from the end user. It's a unified model, which means that, which is especially useful for our use case because we have to run both stream and batch operations consistently, right? Again, partially because this is a new data set. So very often we're coming up with new features, we experiment with features, we say, okay, this feature is a candidate to go into production. So when we put into production, we have to run a new batch job to recompute the entire history so that that feature is available for those who need to use it. So we have to do both batch and streaming operations very frequently. So rather than having one set of code for streaming and another set of code for batch, again, Beam was very useful for us because Beam gave us the ability to write one model. Again, the code is not so transferable. Well, no, that's not true. The code is very transferable, but one model that allows us to be able to use it relatively easy between those two things. There's a slight difference, which again, we're not going to talk about today, about the concept of a window. Again, that's a very important concept for streaming pipelines. But again, we're not going to touch that today because there's a whole lot of things I need to explore to get to that point. One of the other advantages why we went with Beam is that Beam is portable. What do I mean by portable? So there's many considerations that we have to think about in cache. So cache is a heterogeneous environment, and it's heterogeneous from a language point of view. It's heterogeneous from a cloud provider. So we use both Google and AWS, and very often, you're trying to get people to say, hey, this is our requirements. What environment should we use? And that's sort of like a unstable bed that we are standing on. And so again, the advantage to be able to take your code and move it from one environment to the next is especially important to us because it means if for one reason or the other, sometimes it's contract negotiations, Google wants to play hardball or AWS wants to play hardball, we just say, fine, we're going to take our solution and move to the competitor. And you'll be surprised how valuable that ability is, that you're not tied into a specific vendor, is when you reach to those kinds of situations. And so again, Beam is advantageous because it gives us the ability to run on Flink. So Flink is sort of like an open source distributed processing system. I don't want to go too far deep into that, but it also gives us the ability to run it on Spark. Spark is actually very common and very useful for this sort of distributed processing, and the ability to write operations at an abstracted layer that can also be run in a Spark cluster is actually very important for us. And of course, the final point that we liked with Apache Beam that pushed us in its direction is that it was easy for adoption. So again, the barrier to entry was just low. There was some basic concepts that you just needed to understand, which is what we're going to focus on in this presentation. And from there, we just simply started to write those operations, translated our existing code that we use to do our experimentation on, plug them into the Beam operations, boom, we had a pipeline. So barrier to adoption is very, very low. So next question is, well, Apache Beam has a SDKs in several languages, primarily Java, Python, and Go. And Java is actually the most supported language. It started in Java, and Python sort of like came in after the way. So the feature parity is not equal, right? There's a huge amount of features that are available in Java that is not yet available in Python. However, and also a cache organization on a whole actually has a lot of experience using the Java SDK. But in our case, our team, we decided to use the Python SDK. The reasons for that is because, one, our team are primarily ML practitioners. We spend a lot of time in Python, so it was just easier for us to do. We have a lot of experience using Python, and it just made sense from that point of view. Okay, many of us also do a lot of work in Java. You can't get away from Java. Even in a modern, agile, cutting-edge company like Cash App, but even though we use Kotlin, but still runs in the JVM. And Java is very pervasive, and it was just easy to leverage that experience. So that pushed us in the direction of Python. Also, we use a lot of ML tools. So we use Scikit, we use TensorFlow, we use various libraries for data quality and data integration testing that we'll talk about in a bit. And all of that just worked well when your ecosystem was, or when your pipeline, your Apache Beam pipeline is defined with Python. Again, that is not to say that's a constraint. There ways you can get around that, but for us, where we needed to move very, very quickly, that was clearly an advantage. And of course, as I mentioned, we have partner teams. Many of them also have has experience with Python. And so therefore, if we built our pipeline in Python, it makes collaboration with those teams a lot easier. Any questions so far? Great. All right. So one of the misconceptions that we have is that sometimes machine learning can appear to be a, let's see what I'm looking for, messy, random, activity. I don't know. The word's not coming to me right now. That's just the best way. All right. So by and large, a lot of ML practitioners are experimental, so they say, okay, we could just quickly snap together some pieces, do some experimentation, we get a result, and then we could kind of move on. And again, that is not an understatement, but however, when you are deploying solution, especially at the volume and the scale, because as you could appreciate, processing that amount of information is not cheap, right? And what you want to do is to be able to do that in a way that is reproducible, adheres to best practice, is clear, is concise, and you want to be able to ensure that everyone who is working with you has a clear understanding of what is required before we actually sit down and write the code, right? At the same time, those who are familiar with software engineering would know that agility is the name of the game. So you don't really want to spend too long trying to explain to people diagrams and concepts and making sure all the requirements have their I's dotted and T's crossed, right? There's a huge pressure to be agile. And again, so when you're writing any sort of documentation or design doc, you want to be as concise, clear, directed as reasonable as is possible. In that case, what I chose is that I chose to use what is referred to as a data flow diagram. Again, some of you will be familiar with this. If you're not, it's okay. It's really easy to understand. The circles are basically data processing steps, and the rectangles are data stores. That's basically what it is, right? And so it's easy to use these concepts to be able to define what are the actual steps and operations that we want to perform within this pipeline that we are creating. And again, remember, this pipeline is used for both streaming and batch processing. One of the things that we also do in the process of applying engineering into an ML process is that we establish and enforce data contracts. So again, between each step, as data is coming in from the source, as data is moving from one stage to the next, there is a contract that we want to specify. And again, there are different ways that we could choose to do that, but I'll talk a bit about what we chose and why later down in the presentation. And of course, you're writing a production system, and you need to have confidence and trust. And one of the ways that, or one of the tools that we have to do so, is to actually write test cases to say, this is the contract, this is the input, these are the range of input values we expect, or these are the range outs, or these are values outside of the expected input. What happens? Making sure that we can reliably build systems to do so. One of the reasons why that piece is important in particular is because you don't want to run a job that could potentially cost $5,000, which is not an exaggeration, and that failed midway because of some, dumb case that you should have considered. So by having some degree of data contracts and tests helps you to reduce chances of making those kinds of expensive errors. Any questions? Great. So let's take a look at this, at the pipeline. So obviously, let me take a second look just to make sure nothing is is confidential here. Right, this slide took like a really long time to get approved. But long story short, we have data in BigQuery. If people want to know more about why BigQuery, we can talk about that later. But we have data that is being streamed into BigQuery. So there's a stream, BigQuery has a streaming pipeline, and we basically stream in data, and as data comes into BigQuery, it's triggering jobs that are taking in data as streams and passing them through our pipeline. The first thing that we do is that we check that data that is coming in against the schema spec. Right? And one of the reasons why that's important is, again, we don't control what happens upstream. A developer could say on the mobile app, it's like, oh, we want to change this value or do something, and they never tell us anything. And then all of a sudden you get the data that you don't expect, costing the company thousands of dollars, right? So again, you want to have checks and balances at that point. The important thing that we do, just for mention, is that there's a library called Great Expectations. And again, anybody who is doing any sort of like processing for data, especially at a large scale where you want your systems to be reliable, should be using Great Expectation. And maybe that's a whole PyData talk for another time about what a Great Expectation is and what it does, and maybe some examples to show you how it's actually valuable. But again, maybe another time. And then we control for repeated values. So as I mentioned before, we have a lot of duplicates. So again, we filter out those duplicates, and then we do something called enrichment. And so in our use case, we're enriching data. We're enriching the incoming data with data that we have from cache systems. So we have basically huge amounts of data lakes, and we have various processes that put all of that data lake in a form that when that data is coming in through a stream, we can make a quick lookup and say, hey, here's a record that I have. Do I have any information about this user, this customer, this data piece in our cache ecosystem? And if yes, we enrich it, basically merging the two data frames together. And again, we do the same thing with external data. At the end, we have another contract that says, okay, it's the format that is produced in what we expect it to be. And again, one of the reasons why that's important is because we have several team members. I have a team of about 6 or 7 people who work with me, and they're all working on different parts, and we agree on the data contract before to ensure that everybody is working and operating to specification. Again, we don't want to deploy a pipeline. Somebody made a small dumb error, cost thousands of dollars. And I'm stressing this because this has happened. And again, when I say thousands of dollars, I mean like money that you could buy a house, right? Again, because of the volume of data that we're dealing with. And so again, you want to reduce the chances of those expensive errors happening. Again, we have contracts in place to fulfill that. Cool. Any questions? So again, we just use this data flow. Many of you would have seen it before, and you would have been like, I don't know why you learn all these things. I have never used that in our life, right? So again, I'm giving you an example of where it's actually useful and valuable for the purposes of specifying requirements that are shared across multiple teams and help to give people easy, consumable visual representation of the operations that a pipeline is doing before we actually go and start to actually build it. Any questions? Nicholas says DFD takes me back. Nicholas, when you said that, you sound old, right? That was just the other day. Cool. Right. So Beam concepts. Okay, let me take a second look, make sure we're not exposing any Cash App information. And so the first concept, right? So again, you know, we could go deep and we could go wide and stuff like that. So what I'm just going through for the purposes of today's presentation is really what I would consider the minimum concepts that you need to understand to actually start to build a Beam pipeline. So the first concept that we need to appreciate is the idea of what a pipeline actually is, right? And so a pipeline in the documentation is what is referred to as a directed acyclic graph. So again, those who've done, you know, any sort of like work in machine learning for any period of time would know it's almost, we could represent a lot of our experimentation as acyclical graphs, right? So again, that's a very, very common pattern that we see across all the different frameworks that are used for data management within machine learning. And so Apache Beam uses that same concept. And what a pipeline basically is just basically saying, hey, all of the operations that I want to be performed can be grouped together in this simple end-to-end construct. The way to think about it, beyond what the documentation says, is that you can think about it as, what do I actually want to be performed on my data? What is the end result that I want my data to be transformed to? Right. And again, this question is independent of whether it's a batch or stream. Is like, so I have raw data coming in at the end of my transformation. Again, not like a specific step. At the end of the overall process, what do I want? So in some cases, so like we have some use cases at the end of that pipeline is the actual inference results that are stored, you know, somewhere easy for somebody to look up. Right. In some cases, it's an intermediary representation that features that then go into you know, some other machine learning at the point of evaluation. So like the first example is like we have cases where we're generating embeddings. So the graph, there's an actual machine learning model in the step of the graph that takes in inputs and spits out embeddings. So again, you can, what do you want to do? And that operation, that whole series of steps are represented in a pipeline. In the code on the right-hand side, so again, this is code that I pulled from one of our pieces just for the purposes of demonstration. My examples are very GCP specific in this scenario because we are leveraging DataFlow, which I'll talk about in a bit. Even though I don't really have a dedicated slide, but I'll just kind of mention why we use, oh, actually I could mention why we use DataFlow right now. And so in our case, we use DataFlow pipeline. And somebody's asking how Beam performance on non-DataFlow versus DataFlow. I'll get to you in a bit. And so the idea is that for the pipeline, we specify a set of parameters. So where you want the job to run, that's what this runner is. There are different options we could use for runners. So we could specify Spark as a runner, even though it's not called a Spark runner. But we could specify that, hey, we have a Spark environment, and we could specify the IP address where the cluster is located that the job would actually be deployed to. And we could, in the cases of GCP and AWS, there's projects, you could specify that, and you could specify things like your service account. A lot of the data that we deal with falls into the category of PII, or personal identifiable information. So it's a challenge because you have limited access to the data, but machines have unlimited access to all data. So these jobs typically run with a dedicated machine account called a service account and has access to the full data set that it needs to have. And somebody asked a question about why DataFlow, or how does DataFlow compare to other data sources? So in our case, we evaluated several. So we have evaluated Flink. So Flink is basically, again, another. So DataFlow is actually Flink as a service. Though the GCP team might take a little bit of quarrel with me saying that. And again, we also evaluated on Spark. The reason why we went with with DataFlow in particular for our team is that it's only about 5 or 6 of us. So to manage our Kubernetes cluster, so if we were to do it in AWS, for example, we would have to create a Kubernetes cluster and set up Flink in that Kubernetes cluster, and then run our pipeline on top of that Flink on top of Kubernetes. So from a system management point of view, it puts more system needs on top of the team, who are a bunch of like ML practitioners, as opposed to a DataFlow, which is as a service that basically says, hey, let's, here's a job, just run it. And again, it has the ability to scale up and down. We have, in this case, we have like a number of workers that we specify. So in this case, we say number of workers. So there's what you call a cold startup problem. So basically it's like based on how much data that you have, the system will automatically decide how many workers, so workers like a machine inside of a cluster, how many workers to actually start with to be able to process the amount of data that you have, right? So that's basically what that num workers is specifying. It's basically saying, hey, we want a pipeline with 10 workers. That 10 workers is going to be responsible for reading the files from BigQuery. It's going to process that, and it's going to scale up to a maximum of 40 workers. So in other words, as the volume of data grows and the utilization of the machines get exhausted, the cluster in DataFlow can actually scale up and down based on the utilization of the machines within that cluster. Specific to the question of how it compares, that's the primary reason why we use DataFlow, because the convenience of managing versus having a managed infrastructure versus we having to manage it ourselves. But generally speaking, the DataFlow performed well for us, especially when we use what is called, they have a Prime service. In Cash App uses a lot of Google stuff, so we get services before they actually release. But and what the Prime service does is that it allows us to do 2 things. It allows us to do both horizontal scaling. So what I described before of moving from 10 workers to 40 workers, that's horizontal scaling. But it also gives us the ability to do vertical scaling. And vertical scaling says that you have a machine type. So let's say you start off with a machine of like 5 cores and 20 gigs of RAM. It could actually scale up to a higher machine that might have 20 cores and, I don't know, 50 gigs of RAM. I'm just making up numbers at this point, right? But that's one of the options that it gave. So we found using DataFlow, since somebody asked, that the startup process is kind of slow, relatively speaking, relative to like a Spark-backed cluster. And again, that might just be because of the nature of the managed system, but we find like overall our time for job completion is much faster on DataFlow compared to other services. But again, whether that's because of using these new services or just a function of DataFlow itself, I can't really specify that. Sorry to go deeper there than I planned to, but again, somebody was curious to know. Right, sorry. So in that first step, we specify the parameters of the pipeline, where does the pipeline run, the configurations of the pipeline, etc. And then what we do is that we say, okay, hey, pipeline, we want to start with a series of operations. So here we have a text, right? So this text is like a label, right? So this label says, read the entries from packet, right? So we have a bunch of packet files that we use for experimentation with the pipeline. Cheap down reading from BigQuery constantly, and it takes those sets of records, put them into something that we'll talk about just now, and passes it on to the next step in the pipeline. So each of these pipes, so 1, 2, 3, represent steps in the pipeline. So here's the pipeline object starts, and then these 3 operations are 3 distinct steps, which we'll talk about in a bit, inside of that pipeline operation. And again, keep in mind that what depends on the type of runner. So if you use direct runner, that's just on your machine, but it's scaled across different threads or workers, threads or processes, depends on a parameter that you also specify in the pipeline. But if it's on a single machine, it's scales across the number of cores. If it's in a cluster, it scales across the number of workers or number of nodes within that cluster. So again, there's nothing here that I've specified that says anything about parallel. It's just parallel by default. Yep, that's clear. That's understandable. That's easy. This code doesn't look daunting, considering that it's leveraging distributed processing. We just basically say, hey, read, process, write. Cool. And at the end, when we finish specify, so again, Python is a language that is interpreted line by line. However, the pipeline is not actually executed until we say pipeline.run. So we could actually specify the operations and then put like the actual run step as a call that we pass in as a parameter, or put that in the main function and do something with it. Again, it's not actually sent to be processed until this run operation is executed. Cool. So the next, so that's the pipeline. The pipeline gives us the ability to group a set of steps to specify these are the operations that should be performed in our data. That data is kept together in a P collection. What does this P collection stand for? I don't know. Might be pipeline collection. Who knows? Could be. Let's just call it P collection. One of the most challenging things to do in a distributed system is to sort records, right? So that's why I bold unordered, because sometimes when a system is too easy, people lose track of what is actually happening underneath, right? So it is difficult, it's not impossible, but it's difficult and expensive for a distributed system to keep track of order. There are many people who could explain this better than me, but think about it this way. If you have 10 machines in a cluster, and then you take data and you split that data across 10 machines, right? And again, they're running independent processing operations. If you need to sort those operations, then you need to have a way to be able to what we refer to as shuffle the records across multiple workers, and for each worker to know that I have concept A, part A, part B, part C of the collection, to be able to line them up as A, B, C. Again, I really trivialize in a very challenging concept, but the point is, it's a very difficult thing to do. So Apache Beam says, hey, do not assume or do not write operations that require order. The P collection is an unordered bag of elements, right? So basically, as you take things, it processes this collection, and the way that it splits up those operations is totally abstracted from the user. That is handled by Beam, whether that is across threads or across workers in a node, right? It's potentially distributed homogeneous data set or data stream, right? Again, data set in the context of, I have a batch of elements that I'm passing through the pipeline, or stream as I have elements that are coming in one by one to be able to process those records as they come in, right? And again, and what we refer to those two categories of bounded and unbounded, right? So bounded says that there's a fixed size. So based on what we read from big query, it knows that I have, I would say 100,000 elements. So there's a fixed size. So you can say, okay, I have 100,000 elements. I need to process these across 10 nodes. I can create my queue to be able to pass those to the next available queue, and it could operate like that. And again, same thing on unbounded is that as it comes in, it knows the congestion of the network and can therefore optimize to be able to pass those records through as quickly as possible. But again, unbounded data streams require some additional concepts that we're not going to discuss today. Yeah, so that's a P collection. Basically, it's just a group of data, and how that data is represented as it passes through our pipeline, we refer to them as P collections. So P collections is basically the set of all records, thinking about the batch, that we are attempting to process. And as we move from step to step, that P collection may change. So the P collection, the number of values might actually decrease. It might increase, again, depending on the operations that we are doing within that pipeline. The next thing that we want to talk about is a P transform. So plenty P's. You have pipeline, you have collection, and you have transformation. You just put a P in front there, right? What the P transform does is that the P transform represents a particular data processing operation. Now, in abstraction, or if you take a step back, everything is really an operation, right? You could do operations in many different ways. But the way that I think about a P transform is that you could think about a P transform as a process that is applied on a set of records, as opposed to an operation that you do on a specific record. That's a different thing that we'll talk about next. So a P transform says, I'm going to take this collection and I'm going to do an operation on top of this collection. Yeah. So a P transform could take one input as its parameter, but it could also take another input, which we refer to as a side input. It can take side inputs as well, and you could then do interesting things. But again, that's beyond the scope of this talk. The way that we've handled P transforms is that I've sort of set the vision to the team is that we could think of a P transform as a module that we want to use to group smaller operations that are logically related. So for example, in this sample that I have on the right-hand side, we have a P transform that is called canonicalizing an entry, right? Canonicalize just basically means transform it into its canonical representation or standard transformation across multiple record sets, right? So this is just ensuring or enforcing that we discard records that are not canonicalizable, if that's even a word, and we actually do the canonicalize operation. So we take all of those operations, these 1, 2, 3, 4, 5 operations, and we group them together in a single P transform. So in the step of the pipeline, it would just be canonicalized entry, because that's taking in a collection, performing a series of transformations, and returning a collection. Yep. So the series of calculations or transformations that we do will be like reduce, canonicalize, the two things that we're canonicalizing, and any sort of like final reduction that we need to do. So here we take in a P collection as a parameter. So here you have an expand method. We take in a P collection and then we return a P collection. That makes sense? Great. Oh, cool. The next thing is the idea of a PADU. Strange concepts, right? But a PADU is easy if you have spent any time in what we call like a map reduce or map shuffle reduce type paradigm. And again, that map shuffle reduce paradigm is a very common distributed processing system. Again, you can't do any sort of large scale machine learning. Well, I mean, you can't productionize large scale machine learning without, you can't do real-time map machine learning inference on big data without map shuffle reduce understanding. So again, it's just foundational to the field. And what a PADU will do, oh, that is kind of funny. What it would do is that it would take each item in the collection and give it to the operation that you're attempting to perform. So again, remember, the P collection is the set of records. What the PADU will perform is that the PADU will take an individual record from the collection of records and give it to the limit record operation. Yeah. So, and the PADU could emit one, it could emit multiple entries back into the P collection. So what that basically means is that if I use a PyDo, I have choices. I can either, if I get one input, I could return one input. If I get one input, I could return two or more, or I could just return nothing at all. The PyDo allows that sort of like one to many representation or transformations on an individual entry or item in the P collection. So we talked about the operations that a PyDo will do. Every time I say that, I laugh a little bit inside, right? And so they have the concept of a do function. So the do function is sort of like a specific operation that you want to perform on an individual record. So, and I have like a slide that I tried to draw. So maybe I'll start here and I'll come back, right? So the PT is P transform. So you have a collection. Those who laughing at my my diagram, I want to see you all do better, right? You have an incoming collection, and a P transform does an operation at that collection and returns a collection. The PyDo takes in a collection, but takes each element of the collection and splits it across, or takes it and passes in each element into a single do function. And that do function could either return 1, 0, or several outputs for a single input. And then the PyDo will take all of those outputs from the respective do functions, group them back together to return another P collection. Yeah, real easy. One interesting thing to note, again, if you have done any work in languages like Scala or Lisp or any functional construct, you'll be familiar with the idea of a pure function. And again, Beam does not enforce the idea of a pure function, but it's always a good practice to do so, especially in a distributed environment. So that's why in the first operation that we do is that we perform a deep copy of the actual record that we're trying to mutate. So the mutation that we're about to do is destructive, but we don't want to actually affect the incoming data, again, because we don't have visibility into how the groups of data is distributed. So again, it could be distributed across workers, but it could also be distributed across workers and across processes in that worker. So again, it's possible that you could be mutating a record that is also being used by something else at a different stage in the pipeline that is on the same machine, and then that could get messy. So again, you want to eliminate those kinds of concerns, and in that case, we perform a deep copy. Because again, yes, there are cases where Python does pass by reference. So especially if your data set is like your data structure, your dictionary is like very complex, sometimes Python just decides, you know what, it's easy for me to just pass this as a reference as opposed to passing by a value. So mutating that could actually cause a lot of trouble. And yep, the last thing here, again, we then take a single entry, do some operations on that entry, and then we yield the new entry. Again, you might ask and say, well, why yield and not return? Because the do function expects a collection of things. Because remember, as I said before, it's either one or many. So if you return just the entry, it will say, oh, hey, it's an entry. So therefore, this is the collection of things, and kind of screw you up a bit. So yield basically returns what is known in Python as a generator. And since you only yield in one thing once, it has the same effect almost as returning a list of just one item. But yield just looks so much nicer. Yep, great. So final concept, I think, that I wanted to talk today about is the idea of the schema. So I mentioned before that one of the important things that we do is that through the pipeline, we have several schemas that we have defined. In this case, again, because I have a redacted example, the way that Apache Beam requires schemas to be defined is through the use of name tuples. So I have an example of what a name tuple is. Basically, so you have a field, in this case is customer token. That's like our unique customer identifier in cache. And we specify that it's a string. And then we have a series of values that are all strings. What is important here is that this also has the constraint of saying that this that these fields are not nullable, right? In other words, they cannot accept none values. For occupation, for example, I give you an example how you can specify a null value, right? So so all of this is in the concept of Python type-ins. Now, some of you use Python and you love Python so much because you don't have to think about types. And you're like, oh my gosh, why did they introduce types into Python? And part of the reason, again, this is a good example, is that there are cases and scenarios where you need to enforce strong types because you don't want to just allow anything into the data that could have unpredictable results. Again, one could argue and say, well, if it's not typed, then it forces you to have more constraints and handle all the possible scenarios. That's an argument for another day, right? But in this case, we specify that, hey, you can choose either to have a string or none, right? In this case, you could choose to have a list of strings or none, right? This is Python typing that many of you might be familiar with. One of the advantages for data schemes using name tuples and the data schema in Apache Beam is that it gives us the ability to do cross-language compatibility or cross-language transformations. So one of the things that we have not explored yet, but I'm hoping to in the next quarter, is that Apache Beam has the ability to say, hey, you could write part of your operation or part of your pipeline in Java and part of your operation or part of your pipeline in Python. However, when you do things like, you have data that's changing from one system to the other, one of the troublesome components oftentimes in a scenario like that is that you might have problems translating different data types between those systems. So again, the name tuples give us a way, and the data schemas give us a way to be able to ensure that compatibility, especially in the type resolution between those two languages, are maintained. Yep, and yeah, that's basically the core set of concepts that I think are like the minimum starting point and some sample code of how you can put them all together. Any questions? Which is really good because we hit the hour mark, so not too bad.